Right, now, as you look at solving this one, I imagine most of you, when you first see this, are just thinking, whoa, it looks really big and intimidating, right? But oftentimes, whenever you see a problem that looks big and intimidating, a great first thing to do is to try to make it look like something less intimidating. Break it down into something more familiar. Now, if this was a quadratic, our first step would be to move everything to the same side and set it equal to 0. The same is going to be true with this polynomial as well. We're going to move everything to the same side. Now, I'll tell you, when I do my work, I'm going to be moving everything to the right side here. So if you want to be able to have yours kind of look a lot like mine, that's what you'd want to do there. Now, this is what I got once I set it all equal to 0. So remember that as I move stuff over, the like terms are going to be going with the like terms. So for instance, when I move this 60x to the 7th over, I end up actually subtracting that from the 600x to the 7th over here. Then the 64x to the 8th came out of the negative 86x to the 8th. Remember, it's negative 86 minus 64 there. That's why we get the negative 150. And then, of course, the x to the 9ths go together. In this case, I'm adding the 4x to the 9th to both sides. All right, so then once we do that, and we get down to this point, now we got to figure out, okay, what do we do from here? But again, this actually looks like a problem that we've done before, or at least somewhat like a problem that we've done before. Because you'll notice that as you take a look at this particular problem, at this point, it's factorable. And I don't mean by saying what adds to the middle number multiplies to the last number. There's a more basic element of factoring that we can do here. And as you do that factoring, what we're looking for here is, of course, we're looking for anything that goes into every single term. Now, there's two actual layers to doing that in this particular case, because one layer is that we're going to look at just the numbers. And you notice that all of them end in zeros, making it a little bit easier to tell. They're all divisible by 10. So we're going to be factoring a 10 out. But also notice that there are x's in every single term. And so we're going to also need to factor out some x's. How many x's can I factor out of every term? 7. Yep, so we're going to factor x to the 7th out as well as the 10. And remember that when I'm factoring out, I'm not just like dividing both sides by it. I'm not just like getting rid of the 10. I still am keeping whatever I factored out sitting out front of the parentheses when I do that. And again, remember, when we first started this, it just looked big and intimidating. Then we set it equal to 0 to make it a little bit more familiar. Then we said, what can we do from there? Well, we saw we could factor from there. And now that we've factored it, it should now look much less intimidating, because this problem now looks a lot like problems we spent a lot more time with. So hopefully you already know what to do from here. So once we're here, what jumps out to me is the fact that this is a quadratic now. At least inside the parentheses, we have a quadratic. And so I'm going to be now looking to factor that. And factoring that means trying to figure out what two numbers add to the middle number and multiply to the last number. So adding to negative 15, multiplying to 54. Is there such a pair of numbers? Yes, there is. It is negative 6 and negative 9. I've now completely factored this problem. I set it equal to 0, then factored it as much as I possibly can. That means I now can actually find the solutions, because I now want to be able to figure out what can I plug in for x there that is going to make the whole thing equal 0. So what can I plug in for x there that would make the whole thing equal 0? Yeah, 0. Because 0 to the 7th is 0. And then 10 times 0, of course, is 0. So yes, 0 would be there because there's nothing added or subtracted. And then we head over to the other parentheses. So the x minus 6 will give us 6. And then the x minus 9, that will give us 9 as a possible solution. So we're just looking at each of those elements that's being multiplied together. And we're saying what makes those equal 0. And those are our final solutions. And again, I only need to list the 0 once. I did not need to list it out 7 times. Although if you wanted to, technically you could. Now this problem was basically follow-up from last week, where we added on some layers with our polynomial work, and we're building up on it. Now this week we're going to be going and continuing to build with our polynomials, although it's going to look a little bit different, but it is still very closely related to the work we've been doing here. We're we're going to actually be looking at radicals and solving equations that have radicals in them. Now, just to be clear, when I say radical, a radical is a root. A radical could be a square root. A radical could be a cube root. A radical could be a 10th root. Anything that's a root is radical. That's just what that kind of symbol means. They're basically synonymous. It's just that we get so used to saying square root that we sometimes forget that that is actually a type of radical. So just make sure that I don't throw you off with some of the language here. All right, now a lot of these are going to be fairly intuitive for you to be able to solve. Because I'll tell you, the basic idea behind all of these is step one is we're going to get the radical by itself first. And then once we have the radical by itself, we're going to get rid of it. Okay, sounds simple enough, I hope. Now we just need to see how that actually works in application. So for this first problem, we have the square root of x minus 4 equals 5. I need to get the radical by itself. What am I going to do to both sides? Add 4. That's all you got to do. And so I add 4 to both sides. That leaves me a square root of x equals 9. I now need to get rid of the square root. What is the opposite of a square root operation? What undoes a square root? Squaring it. Yep. Because remember, if I had something squared, I didn't undo it by a square root. That means they undo each other. So if I have a square root, that means I want to square it. So I'm actually going to be squaring both sides of this equation. And again, notice the difference between those wordings, because I'll see students sometimes get these mixed up between square root and square. Remember, root has that radical, that little check mark looking symbol. That means root. So if I'm saying the word root, it's got to have that. All right, so we're going to square both sides. And when we do that then, notice I'm actually doing 9 squared. What is 9 squared? 81, yes. Not 3, it's 81. Now, question though. This would make sense because if I do the square root of 81 here, I get 9. So yes, that would make sense that it would equal 81. Do I need to include the plus or minus here? Because earlier we saw that when we were solving something that had squared, I did the square root to both sides. I had to include the plus or minus. So let's take a look and see if the same thing would come up here. So if I do the square root of negative 81, do I get 9? No. The square root of negative 81 would actually be 9i, not 9. And so for that reason, our only answer is 81. We do not include the plus or minus here. So how do you remember when you do need to include it? Because it's not just when there's a square root involved, right? Because this problem includes a square root. You need to include the plus or minus when you insert the square root. This one started with the square root already there. And so we did not need to include the plus or minus. All right, that's the first one done. X equals 81. I think you got the basic idea. Go ahead and do that next one on your own if you haven't yet. I'll give you like 30 seconds for that, and then we'll go through it here together to make sure you got the basic idea down. All right, so in order to solve this, remember my first goal, and whenever I'm solving one of these radical equations, is to get the radical by itself first. So we're going to start by trying to get the square root by itself, which means getting rid of that 3. So I'm going to subtract the 3 from both sides. Notice, I am not trying to combine the 5 and the 3 here. I cannot combine them because the 5 is stuck inside the radical and the 3 is outside of it. All right, I now have the square root by itself, which means I can now get rid of it. So this is the point when we go ahead and we square both sides in order to get rid of the square root. Having done that, you'll notice that whatever was inside of the square root stays exactly the same. And then I square whatever was on the other side. So I end up doing the 4 squared, which is 16. Now it's a very easy equation to solve, I hope. If x plus 5 equals 16, I subtract 5 from both sides. We got x equals 11. And we're done with that one. We're going to continue working through solving radicals as our basic theme for today. It's just you're going to be seeing a few little wrinkles that we throw in along the way, where we take it maybe from stuff that you've seen before to stuff that you haven't seen before. at the very least. All right, so here's two more problems. I'd like you to go ahead and solve both of these, please. So for that first one, again, we got to get the radical by itself first. In this case, that means we got to get rid of the plus 1. So we subtract the 1 from both sides. Now we can go ahead and get rid of the square root. So go ahead and square both sides there. Remember, whatever was inside of the square root, that stays the same. All right, so now we have 3x equals 36. I still want to get x by itself, so I'm going to go ahead and divide both sides by 3. X equals 12. You're done. All right, now on to our second problem on this page. Well, the square root is already by itself, so if you square both sides, you end up getting x plus 2 equals 81. Then we subtract 2 from both sides. You got x equals 79, but there's a small problem with this answer. It's wrong. Notice that if I take this answer of 79 and plug it back into the original equation, which is what I'm doing right here, I'm checking my answer. If I do that here, I end up getting the square root of 89, which is, square root of 81, which is 9, but 9 does not equal negative 9. And yet I followed my process correctly. So what happened? Why does this not work? Well, we're talking about taking a square root of a number, right? Whenever you take the square root of a number, what are you always going to get out of it? Positive. Notice our square root here was set equal to a negative. That's not possible, right? It's not possible for a square root to ever equal a negative number. And so a new layer to our process here. If you ever get down to where the square root, and notice you have to have the square root by itself in order to be able to tell this, otherwise it might become positive with other stuff we do. But if the square root itself equals a negative number here, then you don't even need to go through all of the rest of this stuff. You can just go straight from square root equals a negative to saying no solution. But again, you have to have the square root by itself before you can say that. Otherwise, our adding, subtracting, multiplying, dividing, all that stuff might end up making it a positive on the way to getting the square root by itself. So there's one wrinkle to this whole process. And yes, we will be seeing another wrinkle here down the line as well. But before then, a couple more problems. Please, again, go ahead and write down these two. I'm going to give you a little less time to work on them because there's some potential for questions to come up here. And I want you to have a chance to think about them first, but not get totally just hung up. All right, so let's take a look at that first one here. We have a radical by itself first. That's good. Our first step, if we were trying to solve this, is that we do need to get this radical by itself. We're there. Great. But now that we're there, I have to get rid of the radical. And in this case, squaring both sides will not help us. Because squaring both sides undoes a square root. This is not a square root, it's a cube root. What do you suppose I'm going to need to do to both sides to undo a cube root? Yeah, we cube it. We're going to raise both sides to the power of 3. As a little side note, if this was the fourth root, we would raise both sides to the 4th power. If this was the 7th root, we would raise both sides to the 7th, and so on. So now that we see that we're going to be cubing both sides, now we can go ahead and do that. Of course, cubing, the reason why we're cubing is that it undoes the cube root. So the stuff that was inside the radical is now all that's left behind on the left-hand side. On the right side, I actually do the cubing. So I do 2 cubed, which of course is 2 times 2 times 2, which is why it's 8. All right. Go ahead and finish solving it out from there, if you hadn't quite gotten there yet. And remember, we're trying to now get x by itself. What am I going to do to both sides here to try to get x by itself? Well, I'm probably going to move the 1, right? How do I move the 1 to both sides? What am I doing to move that 1? Am I adding, subtracting, multiplying, or dividing? Well, remember that I want this 1 to become a 0. That means in order for that to happen, I'd have to subtract 1. Which, yes, is what we're going to do. We're going to subtract 1. The reason why I pause a little bit on that step, though, is I know that there are some people who will look at this and they'll say, well, it's subtracting. And so I'm going to undo that by adding. But the reason why that doesn't work is because we would have to undo the subtraction if we were moving the x. But we aren't moving the x, we're moving the 1. And the 1 is positive. But notice that by moving the 1, I still have that minus in front of the x. So it's like there's a negative x there. And so now I have to get rid of the negative. You can either multiply both sides by negative 1, or more commonly, divide both sides by negative 1. It has the exact same effect because it's a 1. This is then your final answer. We got our x equals, so x equals negative 7 here. All right, and then we head on to the second problem on this sheet. And of course, the very first thing we want to do, as always when solving one of these radical equations, is we want to get the radical by itself, which means, in this case, moving the x to the other side. So we're going to add x to both sides. Okay, great. Now we go on to get rid of the square root, which means we're going to square both sides. So we go ahead and we square both sides. And we now have x plus 6 equals x squared. Notice this particular one gave us a very different looking type of equation than the previous ones did, right? Whereas the previous ones just gave us some sort of a linear equation. This one's given us a quadratic. So you'll notice that that work that we did back with quadratics, how do we solve quadratics, starts coming back again. We still have to remember, how would we solve a quadratic? So as I'm taking a look at this equation that I'm left with right now, what's my first step going to be in solving that? Yes, we're going to subtract the x from both sides, then we're going to subtract the 6 from both sides because we want this thing equal to 0. Remember that when we solve a quadratic, unless you can just take the square root of both sides, and in this case we can't because we would just end up right back where we started, we have to set it equal to 0 so that we can hopefully factor it, or if it's not factorable, to use quadratic formula. So I'm really hoping that it is factorable because I don't want to have to use the quadratic formula here. So, is this particular quadratic factorable? Are there two numbers that add to negative 1 and multiply to negative 6? Yes, it is factorable. You should get 2 and negative 3. Therefore, we can then solve it, because remember, this is just the work. The factored form is just the work we use to get there. My answers are actually what can I plug in for x that makes each parenthesis equal 0. So x actually equals 3 and negative 2. All right, this is nice work. There's just one problem with it. It's half wrong. There is another layer to this problem. Because remember how earlier we saw that when we had our square root couldn't be equal to a negative number? It's possible that in this type of problem, like at this kind of a step here, that we're trying to set our square root equal to a negative number because we got a couple different x's as possibilities. And so whenever you have x both inside and outside of the radical. So notice what I'm talking about here. I got the x on the inside here, and I got the x on the outside here. Whenever x is both inside and outside the radical, we need to check our solutions. Which means we're going to plug both of those numbers back in, and we're going to make sure that they actually do work as answers, just like I was showing you with checking that earlier answer, which turned out to not be correct. All right. So let's actually see how this checking process works. First thing I do is I typically will actually write the word check so that it's clear that I'm actually now in the checking process. And then when we check a solution, I'm going to take whatever number it is that I'm checking. In this case, I'm checking the 3, and I plug that 3 in for x. Wherever the x appeared in the original equation. Notice I'm only plugging in one number at a time. I don't plug them both in at the same time. It doesn't work. That's not checking one solution. We're wanting to see, in this particular case, does 3 actually work as a solution? If it does, I'm going to work this down, and I'm going to end up with a statement that says 0 equals 0. If it doesn't, it's going to say something else equals 0. Now, notice I said it's going to say 0 equals 0, because I'm never going to move something from one side of the equation to the other here. When checking a solution, you're plugging it in like you see there, and then you're just evaluating it. You're not solving it. You're not moving stuff across the equal sign. If you move stuff across the equal sign, you run the risk of repeating the exact same action that gave us the false solution over here. All right, so let's go ahead and start working that through. I'm using the order of operations, and so I start by doing the stuff inside of the radical. So the 3 plus 6 gives me the 9. Still sticking with the order of operations, I now will do the radical. Radicals fall under the umbrella of exponents, by the way. And we'll actually see very soon exactly why that is. All right, so now I can go ahead and do the square root of 9. So I got 3 from that. So now I'm going to be doing 3 minus 3. So I got 0. 0 equals 0, which means that that one does work. So I just verified that 3 is, in fact, a solution. Now, sometimes you'll find that both solutions work. Sometimes you'll find that only one solution works. And sometimes you'll find that neither solution works. So you actually do have to check them both regardless of what you get out of the first one. And again, you'll also notice here, I never added this 3 to both sides. That would be solving. That's not what I want to do. We're just evaluating. All right, so I checked the negative 3. We now need to check, I checked the 3. I now need to check the negative 2. So I take the negative 2, and I'm plugging that into the original equation. So I take my negative 2 that I had down here, and I'll plug it in to the original equation. And all we're doing now is we're going to just evaluate that. We're just going to plug it in and see what it gives us. All right, so inside of the square root, if I do the stuff that was inside the square root, negative 2 plus 6, that gives me the 4. If I also do the negative there, the minus the negative 2, that becomes a plus 2. So I did 2 steps right there. All right, next up, let's actually do the square root of 4 then. So then does 2 plus 2 equal 0? No. So you notice here, 4 does not equal 0. Therefore, what that means is that the negative 2 is not really a solution. And since the negative 2 is not really a solution, we can cross that off our list. It is not an actual solution, meaning that the only solution here was actually the 3. And again, I will reiterate, sometimes one will work, sometimes both will work, sometimes neither will work. And you actually have to test them both in order to be able to tell. Do you remember when we have to go through this process of actually checking all of the answers over here? I said it when I first started checking it. We need to check our solutions and go through this whole process that we did over here when x is both inside and outside of the radical, remember. That's a good one to make note of there, because you don't have to do this every single time. You only really have to do this when x is inside the radical and x appears outside the radical. But if you want to do it all the time, you're welcome to. You just don't have to. All right, then one last little nugget of information here. Notice that negative 2 was not an actual solution. It's kind of a false positive after we did our algebra. Answers like that actually come up a decent amount in math. So much so that we have a special name for it. The negative 2 was basically an extra solution, right? It looked like it was going to be a solution, but it wasn't really. It was extra. That's why when we come up with solutions like that that look like they're going to work, but they don't really, we call them extraneous solutions. The root of extraneous is extra. So we just found that -2 was an extraneous solution. That is a term that I will be using going forward, so please make sure that you have this written down so that you know what the heck I'm talking about whenever I reference the extraneous solutions.